An open-loop chain is obtained by bending low-carbon steel rods into the shape shown. For a 160-pound load, determine the maximum tensile and compressive stresses and the distance between the section centroid and the neutral axis. So as we look at this, we got a couple things going on, but this is a classical eccentric loading problem. So what are we going to do? So we're going to find the equivalent centroid load and the bending moment. So we're going to find how to calculate out the axial stress so we can add it to the bending stress. We're going to superimpose the uniform stress due to the centric load and the linear stress due to the bending moment. And then once we do that, we're going to evaluate what the maximum tensile and compressive stresses are. And those are going to be at the inner and the outer edges of the superpositioned distribution. And then the last thing we're going to do is we're going to find the neutral axis. And the way that we're going to do that is we're going to determine where the normal stress of the combined loading is zero. So if there's no point in this that there is a zero stress, so it's not switching from compressive to tensile, then that means that there is really no neutral axis for what's going on. So the first thing I want to do is let's draw a free body diagram. So I have 160 pounds pulling this way. That means internally I have a moment and I have a load that is opposing it. So what do? We'll sum the forces in the y direction. We're going to say those have to be equal to 0. And so I have a positive P minus 160 pounds pulling down. And so that's going to tell me that I have an internal load of 160 pounds. I also need my moment. And as we've seen from the moments before, when we go to sum that up, I've got a moment going in one direction that's resisting the P going the other direction, and that moment's just going to be that distance of 160 pounds, and then I will be multiplying it by the distance, so PD, 0.65 inches, and that's going to give me a moment of 104 pound-inches. So now I have my two forces, so let's calculate things out. So the first thing I'm going to do is my normal stress. And so how am I going to do the normal stress? Well, I'm going to do load stress is equal to load over the area. My load is 160 pounds. If I look back into the problem, I know that this diameter here is 0.5 inches. And so we're going to do pi times c squared. Actually, I was going to say pi c squared, but that would be the radius. Let's use the diameter. So pi over 4 times diameter squared, which is 0.5 inches. And we'll square that whole thing. Let's clean that up a little bit. And so that should be nice, quick. I've got pounds per inch squared, so PSI. And that'll be an 815 PSI normal stress. Computer screwing with me here, but that's okay. And I should have that in the picture. There's my 850 pounds. So now what do I have to do? I want to do my normal stress. And so look at that. So our normal stress is going to be, for the maximum, will be MC over I. So we have to do I first. What do we have? We have a circle. So what is a circle? A circle is a quarter pi r to the fourth. So pi times our radius of 0.25 inches. Raised to the fourth, divide that whole thing by 4, and so I will get an I of 3.068, 10 to the negative third inches to the fourth. Okay, and so our stress, and actually this will be our maximum stress, is going to be equal to MC over I. This one's balanced, everything's right in the middle. So we'll have a positive and negative there. So our moment's 104 pound-inch. Our C value, doesn't matter which way we go, is going to be 1/4 inch. Divide that by our I. 3.068 times 10 to the negative third inches to the fourth. Inches squared on top, inches squared on inches to the fourth on the bottom will leave us pounds per square inch, which is what we expect. And if we bash that out, our maximum stress is going to be 84.75 PSI. Positive or negative, because if we go positive, we're going to be at the tensile stress of the inside. If we go negative, that will be negative 8475, which will be our compressive stress. So now we're going to have to overlay the two of those together. And so the maximum tensile and compressive stress, well, what do we have? So our tensile will be, we just add on the stress. So we've got 815 psi plus 8475 psi. And so our maximum tensile stress will be 9260 psi. And then we do our compressive stress. What's our compressive stress going to be? Well, that's going to be our axial stress minus our bending stress. And so that's going to be 815 psi minus 8475 psi. And that'll give us a compressive stress of negative 7660 psi. So there's the first part. Tensile, compressive. And we have our picture there. Do ignore the fact that the picture says 92. 90, the book made an error. It's actually 9260. Okay, so what's the neutral axis location? Well, the neutral axis location is going to be where my stress is 0. So remember, our combined stress is P over A minus MYI. We're going to be solving for Y. So we can rearrange this and say, okay, well, that means Y is going to be P over A, I over M, because I multiply that through. And then I move all that to the other side. Remember, for the neutral axis, stress is going to be 0. So that goes away. I add over my over I to the other side, multiply through by I over m, because we want to find out what y is at the centroidal. If there is a centroidal axis, we can even call that y0. Okay, so y0 is going to be equal to P over A, which is just our normal stress of 815 psi. Multiply by multiply by the moment of inertia, 3.068 times 10 to the negative 3 inches to the 4th, divided by the moment, 105 pound-inch. I bash all that together, and that's going to tell me that y0, so the location of our neutral axis, is going to be at 0.024 inches above the neutral axis. Sorry, the centroidal axis. And so we're moving in the positive direction, so we are moving towards the negative, towards the compressive side. And so as you can see up here, they even locate the neutral axis for us, because that is where stress will be 0, and you'll notice that it's slid towards the compressive side, which makes sense. If this would have come out to be a negative number, it means it would have slid towards the tensile side.